Hey, welcome to the Tutte colloquium, and it's my pleasure to introduce our speaker this week. It's Michael Brennan from our faculty, and Michael did a PhD in mathematics at Queen's University, and then was off at a special research assistant professor at the University of Illinois, Urbana-Champaign, then went to Texas A&M, and then came here to University of Waterloo, where he has a position in our pure math department and also an associate faculty at IQC. So, I should say Michael loves to run and play drums and talk about quantum.
Yeah. All right, well, thanks very much for the introduction and for the opportunity to give a talk here today. I think it's great how this Tutte colloquium in particular seems to bring so many people from across the math faculty together. And I kind of, I want to talk about an ongoing project with Daniel Gromada, who is from the Czech Technical University in Prague, Roberto Hernandez Palomares, who's a postdoc here at University of Waterloo in pure math, and Nikki Prieb, who was formerly an undergraduate here and is now a graduate student at UBC. And what I'll talk about are Hadamard matrices. And I thought that this was kind of a nice topic to talk about in the Tutte colloquium because it was when a few years ago we were running some learning seminars on Hadamard matrices, and it was the first time where I got to meet actually several people from the C&O department and realizing that there were quite some common interests. So what I want to talk about are, I'll tell you what Hadamard matrices are and how these seemingly simple combinatorial and matricial objects actually give rise to some very mysterious questions and structures which are related to both quantum information theory and something more algebraic, which is quantum group theory. So let me start off by saying a little bit about what is a Hadamard matrix. So I'm going to use H to denote a Hadamard matrix, and so this is an n by n matrix with complex coefficients. Is a Hadamard matrix if two things hold, namely, if I look at its entries, Hij, they're going to all lie on the unit circle. Okay, and the other condition is that its columns, or equivalently its rows, are all orthogonal to each other. Okay? So another way to say this is up to a scaling, H is a unitary. Okay, and the scaling factor, because of the first condition, is always going to be n. Okay? So this talk today is about Hadamard matrices, so H of n. I'll denote by all the Hadamard n by n matrices. So these are the Hadamard matrices. And these are really, you can think of this as like Mn of matrices with entries in the unit circle intersects square root of n times the unitary group of C, right? So this is the collection of Hadamard matrices. So examples, maybe just a few examples to think about. The sort of motivating example in many regards, sort of the most natural example that one might think of is the Fourier matrix. So if Fn is the Fourier matrix in Mn, right? This is right? You take omega to be a primitive nth root of unity, so you could take it to be e to the 2 pi I over n, right? And you look at the matrix whose entries are omega to the ij, where I and j run from 0 up to n minus 1. Okay, so this is essentially, this is the, up to a scaling, this is really the Fourier transform that implements the duality between the cyclic group Zn and its dual, which is also basically the same group, right? Yes?
That H0 is a old one?
So they are complex numbers in modulus 1, right? So they're absolute value, yeah. So they live on the unit circle, yeah. Yeah, so this is the Fourier matrix, and this is, this shows that, of course, there are Hadamard matrices of all different sizes, right? So the most first non-trivial one is this 1, 1, 1 minus 1, F3. Right, F3 is just, well, the Fourier matrices always have ones on the first row and first column, right? And then take the omega squared, and then omega squared, omega, right? And, right, you can write down F4 as well. Omega, of course, being third root of unity here, right? F4. Same thing, 1, 1, 1, 1, 1, 1, 1. And then we have omega squared, omega cubed, right? And you just cyclically go around like this. So it would be omega squared, omega cubed, omega 1. Omega cubed, omega squared. Yeah, I mean, actually, it's a little bit easier if you just write it, right? Because fourth roots of unity, you just write it in terms of I, right? So this will be I minus 1I. Yeah, and then let's write it down. 1 minus 1, 1 minus 1, and then minus I, minus 1, and I, right? So this is going to be the fourth Fourier matrix. And then, I mean, you could do other things, right? So there's actually, you can also take the tensor product of F2 with itself, and this will give a 4 by 4 one. So there's, F2 tensor F2, right? And this is going to be just the Kronecker product. So it'll be 1, 1, 1 minus 1, 1, 1, 1 minus 1, and then 1, 1, 1 minus 1, and then you have negative of the Fourier F2 in the bottom right, minus 1, minus 1, minus 1, 1. Right? So you can do something like this, and actually there are more 4 by 4 Hadamard matrices. There's actually a continuous family of them you can write down, where you just basically look at this I and replace it by a complex number of modulus 1. So H lambda is 1, 1, 1, 1, 1, 1, 1. And, right, yeah, so it'll be lambda minus 1 lambda, minus 1, 1, minus 1, and then minus lambda, minus 1 lambda. Lambda, let's say a point in the unit circle. Right, so you can think of these. And actually, these H lambdas, right, they kind of interpolate between the fourth Fourier matrix and this, what's called a Walsh matrix, which is the tensor product of the Fourier matrix with itself. Yeah? So you can go from, in a sort of continuous way, from this one to this one by just choosing lambda appropriately. So when lambda is 1, you get the tensor product of F2 with itself, and you go the lambda is I, you get the Fourier matrix. All right. So you can see actually just from these examples, the Fourier matrices, or these Hadamard matrices, come in different flavors. So sometimes their entries can be roots of unity and sometimes not, okay? So, so the Butson class of Hadamard matrices so if S, let's say S is greater than or equal to 2, you can consider HS of n, which is the Hadamard matrices whose entries are now roots, S roots of unity, okay? So when I write ZS hat, I really mean this is the collection of roots of unity, okay, of S roots of unity, okay? So, yeah. Which is, of course, a cyclic group, isomorphic to the additive cyclic group. Okay. And so these are what are called Butson matrices, which are a special class of Hadamard matrices. And sometimes you can have Butson or generally generic roots or complex numbers of modulus 1. So an important example is when S is 2. These are what are probably the most famous instances of Hadamard matrices. I don't know, maybe if everybody would agree with this, but these give real Hadamard matrices. Right, and these are Hadamard matrices which have plus or minus 1, of course, as entries. And where do these things come from? Well, they seem to appear everywhere. So why do these come up? Well, of course, Fourier matrices naturally occur if you're thinking about abelian groups and maybe some duality theory and stuff like that for those. But in practice, you know, Hadamard matrices come in mostly, I guess, sort of from more the applied side from communication theory. Which is in the design of error correcting codes, both quantum and classical error correcting code design. There are methods involving Hadamard matrices. In the quantum side, there's something called unitary error bases, error bases. So there's standard sort of tools that are techniques that allow you to start with a Hadamard matrix or a family of Hadamard matrices and build an orthonormal basis of n by n matrices, which consists entirely of unitary matrices. So these are quite interesting sort of algebraic objects that one can use Hadamard matrices to construct. And related to all this is the notion, which is actually equivalent to that of a Hadamard matrix, which is that of a mutually, a pair of mutually unbiased bases. Okay, so what is this? So this is, suppose I have two orthonormal bases, EI and FI, orthonormal bases of C to the n, right? So if I have two orthonormal bases, we call them mutually unbiased. Okay, we call them mutually unbiased if the modulus of the inner product of anything is constant, and it's not too hard to convince oneself that the constant actually has to be square root of 1 over n for all I and j. So we have two orthonormal bases such that their inner products have constant modulus. And if I have two orthonormal bases, of course, they are related by a unitary, right? So EI is U Fi for U a unitary with complex coefficients. And of course, the coefficients of U are exactly these things. So what you get actually is U, this thing that relates these two bases is, I guess, 1 over root n times H for some Hadamard matrix Hn. So for various applications, things like mutually unbiased bases are useful to construct, and they're really the same as looking at Hadamard matrices. Okay, so this is sort of the communications theory side of things. Where I've seen these in my daily life is actually coming from operator algebras. And again, this is really coming from some linear algebraic considerations. So again, suppose I look at the n by n matrices, and I try and I want to look at a maximal abelian self-adjoint subalgebra. Okay. So let's consider a subalgebra, which is maximal, abelian, and self-adjoint. So that is closed under the conjugate transpose, right? So we all know what these are. This is really just the diagonal matrices, okay? So up to a choice of a basis, right? So the diagonal matrices, Dn being the diagonal matrices, choose a basis to represent the matrices, and these are the diagonals matrices. This is an example of what's called a maximal abelian subalgebra. But of course, I can have another maximal abelian subalgebra. They are unital always, so there's always going to be the unit, which is common to both of these. And how are they related? Well, a little bit of effort shows that actually Dn, if you fix a basis, is related to any other massa by a unitary. Okay, so Dn is actually going to be equal to U A, U star, for some unitary in Mn. So unitary. Okay, and then a technical condition that one is interested in coming from an area of operator algebras called subfactor theory, which I won't say too much about, or anything about really, that one wants in order to do some analysis at the end of the day is you want that Dn, take away the unit, so you look at the part of Dn that doesn't, sort of the non-trivial common part. You would like these matrices to be orthogonal to A minus C times the identity. Okay, and this orthogonality is, with respect to the trace inner product in Mn. Okay, this happens again if and only if U is 1 over square root of n times the Hadamard matrix. Okay, H Hadamard. Right, and why would anybody want to care about a square of matrix algebras like this? Well, this technical condition allows you to do something called the Jones basic construction and produce some interesting inclusions of von Neumann algebras, so big infinite dimensional algebras of operators, starting from this kind of nice finite dimensional data. And in a way, the theme of this talk is really kind of related to this, that you start with something that's seemingly nice and simple, like a Hadamard matrix, and you can associate to it certain very complicated and sort of not very well understood objects. And these are related to the theory of non-local games and also the theory of quantum groups, which I want to tell you a little bit about today. So to motivate that, I want to talk about really a little bit like maybe how would you try and classify Hadamard matrices, right? So if I want to classify Hadamard matrices, well, okay, maybe if I look at Butson matrices, these are ones with really finitely many options in every entry, so there's only finitely many. So you could just ask what's the set of all n by n order S Butson matrices, or let's say real Hadamard matrices. But of course, you maybe want to classify them up to some notion of equivalence, okay? So suppose I have a Hadamard matrix, let's say H, and maybe have another one, K, two n by n Hadamard matrices. We say that they are equivalent, so H is equivalent to K, if I can obtain H from K by doing some sort of very natural operations which you would think of as not really changing the Hadamard matrix in any meaningful way, so to speak, okay? So the idea is as follows. These two matrices will be equivalent if, well, if you think about a Hadamard matrix, you look at its entries, you can permute the rows and columns and you still remain a Hadamard matrix, right? You can also take the columns and rescale them by complex numbers of modulus 1 and you'll still be a Hadamard matrix, and you can do that same for the rows. So I should allow all of those operations and get something like, I can obtain, let's say, H from K by performing an index permutation on the rows and an index permutation on the columns, and also multiply rows by complex numbers of modulus 1 and also multiply columns by complex numbers of modulus 1, okay? Where Z, the vector, and W, these are vectors in the unit circle. And so you can think of them as diagonal matrices, and this is really just left and right multiplication by diagonal matrices. And then pi and sigma are permutations. Okay, so these are permutations. So this is sort of the natural kind of operations you would do on a Hadamard matrix without really changing fundamentally what you're looking at in certain ways. So we'll think of these as kind of equivalent. Another way to more succinctly write this is the following. H is equal to U times K times V inverse, where U and V, what are these? These are, they're not permutation matrices, but they are complex signed permutation matrices, right? So maybe these are, we would call them monomial permutations. I don't know if this is standard, but in other words, U is an n by n matrix such that only one non-zero entry in each row or column, and Uij is a complex number of modulus 1, okay? So if you really think about this operation in terms of matrix multiplications, that's exactly what it is, okay? By the way, these these form a group. So the collection of all U's, monomial, right, this is a group, because you can multiply these matrices and they stay having this property. it's a group, and you can think of it in terms of fancy group theoretic terminology. It's actually the abelian group T to the n, semi-direct product Sn, which is also known as the Reith product. No, it goes this way. Yeah, so this is that thing on the right. Don't worry about what it is, but it's by definition, I guess, the thing in the middle. So Sn acts on n copies by just permuting indices, and you get a nice group. Okay. So this is a group, and you really consider, essentially the left-right action of this group on a Hadamard matrix, and its orbit will define the equivalence class. Good. So yeah, so this is what you would want to maybe look at. So the problem is then really to classify Hn mod, this notion of equivalence. And you can restrict this problem. For example, you could do this classification, for example, on Butson matrices, or even real Hadamard matrices in particular.
So Mike, if we do equivalence inside of Butson, do we have
Yeah.
T to the n to roots of unity?
Good question. So if I'm interested in classifying Butson matrices up to equivalence, you can restrict to roots of unity. Yeah. So two Butson matrices are equivalent in this sense if and only if there's one with roots of unity doing it. Yeah, you can do classification on this. And then really, yeah, you're really looking at the group GS, which is roots of unity, free Reith product, or Reith product, sorry. And now this is a finite group. Yeah? So the orbit of anything will be finite, which is nice. Okay, so somehow there's maybe no more of a seemingly manageable structure. But it's a complete disaster. There's like very little known about this classification problem. Good. So for example, it's not even known, for example, for real Hadamard matrices, which matrix size actually contains real Hadamard matrices. So I should mention the Hadamard conjecture. Which is if H is real, well, okay, let me say if I take n and n, for the real Hadamard matrices to be a non-empty set, so we look at H2n to be non-empty, one can do a little bit of analysis to see that n is either 2 or 4 divides n. And the conjecture, so this should have actually appeared above the conjecture. The conjecture is if 4 divides n, then there are real Hadamard matrices of that size. Right? And this conjecture is open currently, as far as I know, at n equals 668. So this conjecture has only been verified for very small numbers. Of course, there are infinite n for which there are Hadamard matrices. You can just take tensor products of F2 as much as you like. And for 2 to the n, you'll get them. Good. So what does this... So there's the question of are there even any? And suppose you're in one of these low n values. So for example, at n equals 28, there are something like 486, I believe, equivalence classes. of real Hadamards at n equals 32, the classification is open. It's been done, but it's huge, right? It's been done, but it's, how many? 13 million, that's right. Okay, it's done. Is this this paper by Caligari?
No, Caragani.
Caragani? Okay. Okay, so that was, so, okay, I guess my knowledge is a little out to date. This is done, and yeah, there's approximately 13 million. Yeah. So, so even for these, real Hadamard matrices, never mind Butson or general, the problem is very far from, it's a hard problem, right? Here, just at 32, you have 13 million, approximately. So this is bad. Not so big. For a simpleton like me, it is. Yeah.
And then analysis locally would be very impressed.
Yeah, that's right. Yeah. Okay. And for general Hadamard matrices, so the classification problem is done for n equals 1, 2, 3, 4, and 5. There's only one equivalence class at each of these levels, and it's the Fourier matrix. Right, the equivalence, everything is equivalent to the Fourier matrix for all of these ones. For 4, it's the equivalence class of this family that I wrote down, H lambda. Lambda going from 1 all the way up to I on the unit circle, not all the way around. Okay? So there's an infinite family here, and then back at n equals 5, there's not just 1 again. This is, this step at 5 is challenging. This was done by work of Uffe Hogerup in the context of this subfactor program. But beyond 5, at 6, there are infinitely many families of general Hadamard equivalence classes. Okay, so what was the point of all this? It was to sort of say, well, maybe you want to try and classify Hadamard matrices up to a fine or a more coarse invariant, and this is what is known as quantum equivalence, which is it's going to be coarser than usual equivalence, okay? And it will be denoted by quantum, or an equivalence with a Q, okay? And there's 2 ways that you can formulate this, which are actually equivalent. One is using the language of interactive protocols, non-local games. And the other is using more algebraic language. And I'll try and say something a little bit about both. So I want to introduce what is usually, or what we call the Hadamard equivalence game. Okay, so here's the situation. I want to suppose I'm interested. I have 2 Hadamard matrices, and I want to somehow determine whether they're equivalent or not. Okay. One way I could do this, if I have 2 people, 2 players in a game, I can query them in a certain way to sort of see if I can get a reasonable confirmation that something like this is true. Okay. So the idea is as follows. So there's a referee, and then there's 2 players, Alice and Bob, okay? And the input is the information of 2 Hadamard matrices, H and K. And for this, I want to think about order S Butson, okay? Okay, so these are Hadamard matrices where we have order S roots of unity. Okay? And the idea is that these two players are going to try and convince the verifier or the referee that these are equivalent matrices, okay, in the sense of Hadamard. So what I do is I'll do the following. So there will be, the referee will pose questions. And the questions will consist of rows, R1 up to Rn, and columns, C1 up to Cn, of the given matrices. So R1 denotes rows, C1 denotes row 1, etc. Okay, so these are inputs. These are the questions. And the answers, so if a player gets a question, a row, then they're going to have to respond with a pair consisting of a row or a column and a root of unity. Okay? So the answers in this game are going to be given by rows and roots of unity. Rows are columns. Okay, and how does this work? So the rules of this game, so here the situation is as follows. You're going to have the referee, and they're going to, let's say, randomly select a question, a pair of questions from the inputs, let's say uniformly, and they'll pose them to the players, Alice and Bob, and then they're going to somehow, with some predetermined strategy, figure out how to reply A and B, okay? And now, how is this going to look? So suppose if Alice and Bob get the same question, they need to provide the same answer in order to win a round of this game. So this schematic here is representing one round of this game. Okay? So that's something we would naturally want to have happen. The second is if, let's say the referee gave row I to Alice and column J to Bob. Then the answers would be we want, so in order to win, another winning condition for this game of a round would be if I get a row, I should answer with a row. So maybe row K. And then I will have some complex number, some root of unity Z of modulus, some root of unity Z. Okay? And similarly, Bob, right, is going to give, if it gets a column, they will get, they'll have to reply with a column and another complex number of modulus 1. Okay? And the requirement here is that for this input ij, I should have hij is equal to z, k, and then we have k and l, w inverse. Okay? So under the condition that they receive a row and a column, then they have to reply with rows and columns, and then you can ask this question, does this sort of thing happen? Okay? And so this is the game. Same questions have to return the same answers. If they got a row here and a row here, then we don't care what answer they give. Okay, so they just win the round in that case of that game. Okay, and so if you were to try and understand the player's behavior, well, we're going to impose, of course, something to make this interesting, namely that the players don't communicate. So there is no interaction between the players. They have no idea which questions or answers each one gave. Okay? But to the observer, all right, the strategy of Alice and Bob in playing collaboratively in this game will look like a statistical behavior, right? It'll be a correlation. Okay, so this is going to be a correlation. Right, of answers A, B given questions X, Y. So this is a correlation. Right, so questions X, Y result in whatever answer they give, and then they have this behavior with some probability if you sort of observe multiple rounds of this game. So this is a correlation, and it wins. We call it winning or perfect, I guess I should say. It's a perfect correlation if it wins the game every round with probability 1. So if a tuple A, B, X, Y results in a losing scenario, then the probability of A, B given X, Y is 0. Okay, so that would be a behavior that indicates they're playing this game very well, okay, and they're winning every time. So in particular, every time this situation arises where one gets a row, one gets a column, they return their answers, then this sort of local verification of Hadamard equivalence is satisfied, then you'd be sort of reasonably convinced, okay? And I guess I should mention, so deterministically, they could play this game, right? A deterministic so a correlation could be deterministic, and that would really just be, a 0-1 valued correlation. This correlation, P, would correspond to a pair of functions. Well, actually a bunch of functions. So we'll have pi and sigma maps from 1 to n to itself. And basically, Z and W functions, vectors in the unit circle. Right, what you do is if you get an I and a j, you reply with pi of I and pi of j and Zi and Zj, okay? So a deterministic behavior would be specified by functions. And it's perfect if and only if, well, this is a permutation, and that's a permutation, okay? So perfect if and only if H and K are equivalent as Hadamard matrices, okay? So due to lack of time, I won't say much about other correlations you can build, but there are quantum correlations which somehow use entanglement as a resource. Okay, so it's possible in certain games. So you can generate physically quantum correlations which are perfect. Okay, so that is, you can maybe have instances where these matrices are not equivalent, but you can still convince a verifier that this is true. Okay? Right, this is, usually the language is phrased as you have maybe a finite dimensional or an infinite dimensional Hilbert space, a state vector, and families of commuting projection value measurements, which can be used to realize bipartite correlations. And if you're lucky, you find one that is perfect for this game. Okay? So there are quantum correlations which are perfect. And in this case, we say that these things are quantum equivalent. Okay, so H is quantum equivalent to K. And an easy observation is if you are equivalent, then you are quantum equivalent. And the natural question is, if or when do we get implications the other way? This is, in general, not true. So in a sense, you get an equivalence relation on Hadamard matrices, which is coarser, possibly coarser. Okay? So let me state a theorem. Actually, I need a little preparation. So definition. I want to give a algebraic formulation of quantum equivalence. So definition, if H is a Hilbert space, okay, and I have U, an n by n matrix with entries in B of H. Okay, so it'll look like this, Uij. Okay, this is a quantum S monomial matrix if the following is true. 1, U is unitary. 2, so unitary, what does that mean? This is an algebra of operators on a Hilbert space H tensor C to the n, so you can talk about unitarity. The other thing is I want U transpose to be unitary, so I take Uij and replace it with the matrix with ijth coordinate Uji. I want this to be unitary. The third condition is that Uij is a normal, so it's a normal operator. So normal means it commutes with its adjoint. And the common thing, Pij, we ask that this be a projection. So an idempotent. So where is this coming from? Again, think about matrices whose entries times their conjugate, if they're scalar, they're 0, 1 valued, right? So these are looking like, kind of like matricial or operator analogs of monomial matrices. And then the fourth condition is that I want I would like some order S type condition. So I would like Uijs to be Pij. Right? So these are the 4 conditions. Okay? And the theorem, 2 Hadamard matrices of Butson class S are quantum equivalent if and only if there exists a quantum S monomial matrix U over some Hilbert space such that H inverse U times K is also quantum S monomial. All right? So whatever this game is, whatever quantum strategies are, you can forget about all that because that condition is actually equivalent to this condition, which is an algebraic one, or operator algebraic one. And the important thing to note is when U has entries in B of C, namely it's an actual matrix, you're really just looking at monomial matrices, and this condition is exactly saying that H and K are equivalent to each other. Okay, so this is weakening the notion of equivalence. Right, so I'm out of time, so maybe in the last, I'll steal maybe 3 minutes, let's say. I want to mention, so this sort of turns the following, so that you get an algebraic question. Given two matrices, H and K, I can consider the following universal algebra. So this is going to be a star algebra. I'm not thinking about operators on Hilbert space or anything, just star algebra, generated by some indeterminants xij, I and j going from 1 to n, such that the matrix of these generators and H inverse xk are quantum S monomial. Okay. A question is, when is this algebra not zero? And this is, again, this is a question now that you can think of as purely in the realm of, algebras with generators and relations. When is this algebra not zero? The non-zeroness of this algebra is actually equivalent to there being a Hilbert space realization. So the question of identifying equivalence, or this generalized equivalence, really comes down to a question of when our algebra is not zero. And let me just end with the part that in my abstract came first, but I will not talk about, I guess. So let me just say, A, HK, this is some sort of non-commutative space of equivalence between H and K. If H is equal to K, HH, now you're looking at, this is actually something very special. This is actually a Hopf algebra. So it comes with some additional sort of co-multiplication structure. And this is really, you should think of this as the quantum symmetry group of a Hadamard matrix. So let me just say, there are tools, there are sort of, once you have some sort of group-like objects around, there are often tools that are at your disposal to determine whether something like AHK is non-zero. So you can, in certain cases, determine the non-zeroness of this sort of quantum isomorphism algebra from the representation theory of the quantum group AH. Okay? So this representation theory is really some sort of tensor category that you can get. Okay? And, well, I'm out of time, so let me just say two things. The first is, when you have a real Hadamard matrix, this is a result of Gromada from 2023. All real Hadamard matrices are quantum equivalent. So 13 million at index 32 collapses to one equivalence class, for instance. And so in follow-up work with Daniel, we looked at the case of higher order ones. And the jury's out, more or less, on what happens there. We can show that there are definitely inequivalent Butson class matrices of prime order. And the way you do that is essentially by looking at the representation category of these Hopf algebras and doing some essentially linear algebra. So I guess I'm out of time, so I'll stop here. Thanks very much.
Thank you very much. So, time for some questions.
I'll make one small comment. It's meant to be local, but that result of Romano was proved independently by Bill Martin and Ada Chan.
Yes, so I should mention, this result about equivalence of Hadamard matrices for real Hadamard matrices, there are graphs that you can associate to them, and then the question really becomes a question about quantum isomorphism of graphs. And yeah, this was proved independently of Daniel by Ada Chan and Bill Martin, who are alumni of Waterloo. Yeah.
Okay. Any other questions? Oh, thank the speaker once more.